So for this week, we're doing our very first Helio Mission Highlight. So our mission for this week is the Parker Solar Probe, and I'll give just a little intro. I don't want to spoil too much, but it launched in August of 2018, and it's going to be a 7-year mission that completes multiple orbits around the sun and is collecting solar wind data. And the probe made its closest approach of any satellite to the solar surface on December 24th, 2024. And today we have our speaker, Tamar Ervin, joining us. Tamar is a second-year PhD student in the Department of Physics at UC Berkeley, working with Dr. Stuart Bale at the Space Sciences Lab. Tamar is a member of the Parker Solar Probe and Solar Orbiter Science team, working on the source regions and heating mechanisms of the solar wind. She worked on the Foxy 4 sounding rocket campaign and is the Electric and Magnetic Fields Instrument Suite (PI) on the upcoming OSHR sounding rocket mission scheduled for launch early 2026. And fun fact, she was also awarded the Big Bang Theory Scholarship Endowment and got to meet the cast on set. So please welcome Tamar.
Sick, thank you. Okay, I'm gonna share my screen. If my Wi-Fi cuts out, I'm really sorry. I'm at this meeting called Shine in South Carolina, and I don't know. Well, one, the meeting runs for 12 hours a day, which is rude, and two, the Wi-Fi is really bad. So, yeah, if I stop functioning, just let me know. Okay, so yes, hello, I'm Tamar. I'm finishing my third year now, so you can tell I don't update information about myself on the internet. But yeah, I work at Actually, if I undo this, I had this about me slide, but it's irrelevant. But yeah, I work at Berkeley, um, which is cool for various reasons, most notably that it's very pretty and our lab overlooks the Bay Area. But from a science perspective, because I get to work on PSP. So Parker Solar Probe, or PSP, is an inner heliospheric spacecraft that's studying the solar wind and the solar corona, as we'll talk about in a moment. And it is a mission concept that has been sort of thought about and developed for multiple decades, like longer than probably most of us have been alive, to be honest, which is pretty crazy. And what ended up with was this beautiful spacecraft here that's flying through the sun's outer atmosphere to study a variety of open science questions. So a little bit of history. Eugene Parker, who maybe some of you have heard about, predicted the existence of a supersonic solar wind, actually sort of any sort of stellar wind coming out of sort of a magnetized star. And so there was lots of theoretical work thinking about the solar wind, and it was later sort of observationally confirmed by a variety of spacecraft flying inside the heliosphere. But because of this sort of prediction and this mathematical work, there was this sort of report from the Simpson Committee to the Space Studies Board. So these were all sorts of like agencies and entities that existed before we had sort of the setup of NASA and the national academies. But they essentially recommended that the United States build a solar probe or an outer solar system probe to sort of study the solar wind. And this took sort of 50 years of different sorts of studies. We like this video that shows sort of some of the different concepts and shapes of the spacecraft until it turned into what PSP actually is today, which you'll see in a moment. This is what our lovely spacecraft looks like now. It launched, in 2018, and through a variety of gravity assists around Venus, flew the closest to the sun of any man-made object. So we're interested in studying sort of this near-sun environment, and this is very much an engineering challenge. So the sun, as we know, has sort of light and radiation, and it also is very, very hot. So flying close to the sun has sort of a variety of issues that spacecraft closer to Earth don't have to deal with. So in addition to providing really, really cool science, Parker Solar Probe also sort of this huge engineering challenge and now feat of engineering that we were able to get a spacecraft so close to the sun to actually make usable scientific measurements. So if you're sort of interested in the engineering or technological side of this, there's sort of a lot of instrument papers that I'll highlight later talking about some of the new advancements that the engineers made to be able to actually make measurements this close to the sun. All right, next slide. So this is PSP. We have a website. It's listed here. If you just look up Parker Solar Probe, you'll probably find our website. We're hosted on the Johns Hopkins Applied Physics Lab website. So APL is sort of the science hub for PSP. So you can find all sorts of information about the mission here, as well as sort of updated information about how fast the spacecraft's moving, how far away it is from the sun, and most interestingly, how hot the heat shield is. So as you can imagine, if we're flying really, really close to the sun, the temperatures are going to be really high. The solar atmosphere is about 1,000,000 degrees, and flying metal in 1,000,000 degrees that you want to make measurements with is obviously a challenge, like I mentioned, because you don't want things to melt. So we have this really cool heat shield here. I'll show a couple pictures in a moment. It was sort of it's like feat of engineering that was able to actually protect all the instruments that are behind it from the heat and radiation coming from the solar atmosphere. But there's lots of cool information on this website. If you're also sort of interested in participating, since you're all early career folks, you can make an account on the Science Gateway up here. Twice a year, we have early career focused online meetings. They last for 3 days. We have people presenting from all over the world, and it's just students and early career scientists. You can also email me if you have any questions. I run those meetings alongside a couple folks at Harvard and in Europe. But yeah, you just make an account here on the Science Gateway. Okay, moving on from logistical things. PSP launched in 2018. Okay, you could hear it. I didn't realize you could hear it. I don't know how to mute it. Okay, there. But maybe I can just hear it. Anywho, this is a video of the launch of Parker Solar Probe. It's very exciting. You're going to see it's going to make a very large explosion. And then we'll talk about science. I just think rocket launches are so cool. Okay, very good. There it goes. All right, so there was all this work, sort of 50 years of scientific work, engineering work that all culminated in this launch of the spacecraft in 2018, leading to the science that I'm going to talk about. And if you have any sort of engineering related questions, there's also more information on the website as well as the science papers. There it goes. Yay. Okay, so Parker Solar Probe is a spacecraft that has sort of 3 primary science goals. We're interested in tracing the flow of energy that heats and accelerates the solar corona. So for context, I'm sure most of you know, but the solar corona is sort of the outer atmosphere of the sun. A stellar corona is the outer atmosphere of any star. So a lot of the things that we can learn from PSP can be applied to other stellar systems. We're interested in studying the structure and dynamics of the plasma and the magnetic fields at the sources of the solar wind. So the solar wind is the continuous outflow of magnetized charged plasma from the solar atmosphere. Other stars have stellar winds. And one of the sort of open questions in astrophysics in general is sort of what drives these winds? How are they heated? How are they accelerated? And where topologically on the solar surface do they emerge from? So similar to how Earth has mountains, valleys, water, the sun is not smooth. It also has sort of topological features. These features, rather than being driven by sort of geologic activity, is driven by magnetic activity. And so we're really interested in understanding what is the structure and dynamics of the fields at these solar wind sources. And then lastly, we're also interested in exploring mechanisms for particle acceleration and transport, specifically of energetic particles, primarily because of the impacts that these energetic particles have on satellites, spacecraft, and astronauts in space. So I have a couple of pictures here. On the left side is a full-scale model of Parker Solar Probe. A lot of the stuff on here are actually engineering models. So they were sort of the flight spares. If you are ever in DC, this is shown in the Smithsonian Museum, the Air and Space Museum, I guess. It was shown at AGU last year, which is a really big scientific conference, but it's been in the Air and Space Museum ever since. And these are some observations of the solar wind that you have to show in every talk you ever give about the solar wind, that really just shows, this is a measurement of the solar wind speed. And so you can see that depending on sort of where you are relative to the sun, you get large variability in the speed. Sometimes we have fast wind, sometimes we have slow wind. You can also see this is during the first orbit of Ulysses. This is during the second orbit of Ulysses. You see that sort of the variability in the solar wind speed dramatically changes, as well as sort of the variability of the density structure, the magnetic field structure that we see from the remote observations in the background. And so sort of these variabilities through time and through space are some of the things that we're trying to study with Parker Solar Probe. Okay. Also from Earth, if you ever get the chance, you should go check out a solar eclipse. But so this is a simulation of a solar eclipse. But if you could see the solar eclipse with your eyes, what you'll see are sort of these structures that are sort of emerging from the sort of outer atmosphere of the sun. And this is what makes up the solar corona. So this is actually the region that PSP is flying through. And this is the region that we're interested in studying. All right. So How do we do this? So Parker Solar Probe has a very unique trajectory. A lot of you might have heard about or worked with spacecraft that sort of orbit Earth. Very often when we have a spacecraft in Earth orbit, we put it at one of the Lagrange points, so that way it can stay sort of in a relatively gravitationally stable orbit. But Parker Solar Probe, as I've been mentioning, wanted to actually fly through the sun's outer atmosphere. And so this required a sort of very different type of orbit. So throughout the sort of conceptualization of the mission, there was lots of talk over like, how should we do this? One of the first ideas was to use a gravity assist. So essentially, you launch your satellite and it shoots itself around one of the planets to change its orbit into the sort of inclination and location that you want it to be at. Primarily because we can't directly place a spacecraft in the orbit of the sun with like a rocket. So one of the first ideas was actually to have PSP do a gravity assist around Jupiter, which would basically mean that, you know, here's the sun, here's Earth, here's Jupiter. The spacecraft needs one complete orbit would be from sun to Jupiter. So very, very far. What they ended up sticking with was doing gravity assists around Venus. So what you can see here is the orbit of Parker Solar Probe. So PSP has had 7 gravity assists. Our last one was last November. And now we are sort of flying actually within the orbit of Venus. So Parker Solar Probe has sort of an elliptical orbit that flies very close to the sun at 10 solar radii in its sort of innermost portion of the orbit, and then out a little bit within the Venus orbit in the outermost portion of the orbit. During these 7 times that we passed really closely to Venus, we can also do actually a lot of Venus science. So if you're ever interested in sort of synergies with planetary science, there's a lot of interesting stuff that the team has done as well. Okay, and then this is sort of a plot of how the spacecraft's distance from the sun has varied as a function of time. And so we see that, you know, we started far away from the sun, we get pretty close, and then over time, our closest approach to the sun has gotten closer and closer until we actually were flying through the sun's outer atmosphere or directly through the corona at 9.8 solar radii. So if you imagine 1 solar radii is the sun's outer atmosphere, 9.8 solar radii is 9.8 times away from that. For context, Earth is 215 solar radii away from the sun. So we're like very, very close to the sun's surface. And so how do we study this? So I mentioned that we have sort of these 3 science questions. We're interested in studying the heating and acceleration processes, the structure and dynamics of the magnetic field, and acceleration and transport mechanisms. So we do this by making observations. We make sort of 3 primary types of observations. We study fields, so we make measurements of electric and magnetic fields. We also study waves and radio emissions. We make measurements of particles. So we study particle distribution functions. We're interested in how, what are sort of the particles' energies, what are the types of particles that we see. And these 2 types of observations are known as in situ measurements. So this means that we collect data with sensors that are sort of physically touching the plasma. So you have a spacecraft flying through the plasma. It has a magnetometer on it that can make a measurement of the magnetic field. And that in situ measurement is the measurement of the magnetic field specifically at the location that the spacecraft is at that specific point in time. So these in situ measurements tells you lots of information about the plasma at time and the location of the spacecraft, but not necessarily about sort of the global structure of what's happening. So if we want to understand sort of the more global structure of the corona, we need remote observations. So remote observations are when you measure things from a distance and you have no direct contact with the thing that you're measuring. So these are any sort of picture type, image type observations. So if you're working with observations from like the Solar Dynamics Observatory or ground-based telescopes like DKIST or anything like that, these are sort of remote observations, whether you're looking at the sun or other sort of astro objects in white light, invisible wavelengths, UV wavelengths, these are all sort of like remote observations. So PSP takes wide field white light images. So this allows us to sort of image the actual density structure of the corona. And I'll talk a little bit more about these instruments in a moment, but essentially with the combination of these sort of different types of instrumentation, the hope is that we can close on our science questions. So the in situ measurements will allow us to study sort of the heating and acceleration and transport processes, and the remote observations will allow us to do sort of connection between what we see in situ and what is actually happening on the solar surface. And so this is what the spacecraft looks like. So I'm going to show sort of 2 photos of this, one from each side. So we have the TPS, or thermal protection system, which is our heat shield. So PSP has this really weird orbit, but essentially the spacecraft is always rotating such that this thermal protection system actually faces towards the sun and protects all of our instruments. We have the solar arrays. So these are our solar panels such that we're able to sort of power instruments. There's some antennas, a cooling system, but we also have a variety of instruments in the spacecraft. So one of them is the solar probe cup. So this is the Faraday cup. They make measurements of particles. And then we have one of the proton and alpha particle sensors over here. On the other side of the spacecraft, we can see all sorts of other instrumentation that we have. So we have magnetometers. So magnetometers there's a couple of different types on probe, but they can make measurements of the magnetic field. We have the fields antennas. These make measurements of the electric field. It's actually a very simple concept. You basically have a probe on each end that can make a measurement of the electric potential. And then you use the fact that the electric field is equal to the electric potential divided by the distance between the antennas, and you can get a measurement of the electric field. We also have our wide field imager here. And so the spacecraft has sort of all sorts of instrument suites on it. And something really cool about PSP and a lot of NASA missions in general is that there was sort of a lot of collaboration, both in the United States and internationally, to build all these instruments. So for example, the electric field instruments and the span, electron and ion ESAs were built at UC Berkeley, but the magnetometers, for example, were built in France. The wide field imager was built at the Naval Research Lab. These telescopes were built at a combination of sort of US and European institutions. So, working in science is a great way to have international collaboration as well as collaborators all over the country. And it's very cool because you get to meet all sorts of different types of people. So I'm going to briefly talk about some of the instruments. So I mentioned that we have the field suite. So fields, the PI institution is Berkeley. We have a flux gate and search coil magnetometer, so we can make really high resolution measurements of the magnetic field. We have a radio instrument. This allows us to study waves, look at radio emissions from the sun. So if you're interested in studying, for example, radio bursts associated with transient events like flares, we can also get measurements of the electron density and temperature. And we also have these sort of electric field instruments that make measurements of the electric field. SWEEP is the suite that studies sort of makes particle measurements of sort of low energy particles. So we have the ion and electron solar probe analyzers. So these are what is known as their electrostatic analyzers. So ESAs, it's a very common type of instruments. They make measurements of distribution functions on this grid. And you can do different types of integration to make to get partial moments of the distribution function. So essentially you can measure like density. So how many protons are in sort of a cube of space, how fast they're moving, and what their temperature is. There's also a Faraday cup that does the same thing, but it only makes 1D measurements. We also have WHISPER. So this is, the prettiest thing to look at. So WHISPER is a remote instrument that makes white light images. So it actually has two fields of view. So this is the inner field of view here. But so essentially it has like an inner and outer field of view with cameras. Oh, that got a little blurry. That's making observations in white light of the corona. So this is the spacecraft actually flying through the solar corona, and you can see a variety of things here. So they're white light instrument or white light measurements. So they're essentially measuring density. So if it's brighter, there's more stuff there. And you can see lots of stuff. So you see continuous outflow, which is the solar wind. You can see some eruptions of plasma associated with coronal mass ejections. You can see some inflows that people are still studying. And you basically see that this is a very sort of dynamic environment with lots of structure. All of the structure is associated with the magnetic field, and understanding sort of the dynamics in these structures in the magnetic field is one of sort of the main science goals of PSP. So WHISPER sort of takes direct observations of the solar wind. It studies shocks, transient events like eruptions, and also, I'll mention at the end, but it discovered or observationally confirmed the fact that we sort of have a dust-free zone really close to the sun. So as some of you might know, there's a lot of sort of dust in the heliosphere. There's a lot of dust in space. Dust is really, really problematic for spacecraft. If dust hits your spacecraft, it can cause electrostatic issues because it can be charged. And so sort of understanding what the dust environment is wherever we send spacecraft or wherever we send astronauts is really important. And so one of the things that the WHISPER team is and the electric and magnetic field instruments are really focused on is sort of understanding the composition and sort of the location and density of heliospheric dust between Earth and the sun. Okay, and then the last instrument we have is ESIS. So ESIS is an energetic particle instrument. So they measure energetic protons, electrons, and heavy ions. So these are things that are moving faster than just the background solar wind. And so these sorts of things come from really energetic events on the sun. So for example, solar flares and coronal mass ejections can produce really energetic particles, and understanding sort of the distribution and the acceleration and transport mechanisms for energetic particles is one, an interesting science question, but two, really important for sort of protecting our assets in space. So here is a fun NASA visualization studio video showing a spacecraft being bombarded by solar energetic particles. And oh, it froze itself, but you can see that they're charged and they can cause damage to our spacecraft. So being able to sort of accurately model what the transport of these energetic particles will look like is really important as we sort of send more spacecraft up in sort of these constellations like Starlink. And to be able to accurately sort of model and predict where we expect these things to be in the heliosphere requires us to have a good sort of understanding of the basic science. And so this is one of sort of the primary science goals of PSP, and one of the things that a lot of the folks on the team are working on. Okay, I'm going to take a pause. Was there anything that I said that people had never heard about before? Any questions that people have? Otherwise, I will just keep talking.
You mentioned the space dust, and that they're trying to figure out the composition. Is there a typical composition of this? Typical elements.
Were you asking? Yeah, that's actually a good question that I don't really have the answer to.
Okay.
But I can point you to some papers. I don't personally work on dust. So I honestly don't know. I know that in general, the dust particles are larger than sort of the ambient wind, but what they're actually made of, I don't know, and I should figure out, and I will find out and let you know.
Okay.
If anyone else knows, feel free to chime in.
But it's not the same as interstellar.
Someone at Berkeley definitely knows.
Yeah. Okay.
Claire will know, because Claire worked on dust before she switched to working on the ionosphere. Okay, any other questions? Do people know what coronal mass ejections and flares are? Or am I just spewing words that folks have never heard before?
There's a thumbs up here from Aria and Marcus.
Yeah.
Hello.
Hello, yes.
Hi, Tamar. I have a question about these energetic photons, electrons, and heavy ions. Are they always accompanied by solar flares and coronal mass ejections, or not always?
Yeah, so there are sort of a variety of ways that you can energize and accelerate your particles such that they're what we call energetic and are detected by this instrument. The primary ways are either at the sun, so they're energized by flares, or sort of in transport throughout the inner heliosphere, in which case they're typically energized by shock structures associated with the propagation of a coronal mass ejection. So here in this video, you could see if it comes, the CME propagating. It's sort of this loop-like structure. And because it's moving much, much faster than the ambient background wind, it's going to produce a shock. And that shock structure, shocks in general, are really, really good at accelerating particles. So this is one of the ways that we get energetic particles. This produces a shock in the same way if you've ever seen a video of like a plane going supersonic. It's a very similar idea. You're going to produce sort of a shock structure at that fast, slow boundary.
Thank you.
Mm-hmm. But yeah, in general, like how exactly these protons and electrons and ions are accelerated is very much an open question. There was so at the meeting I'm at, there was like a big session about this yesterday for like 4 hours, and it's still a very hotly debated topic. So yes, they hit the spacecraft. This is bad. So we want to be able to prevent this, predict this, and to do that, we need to have sort of basic scientific understanding, or what are the processes involved in sort of energetic particle transport. Okay, this is the end of my discussion of like the instruments. Now I'm going to talk about some of the sort of new discoveries and open questions that sort of the Parker Solar Probe team is trying to answer. Specifically, maybe you all can think about what you find interesting. You know, this could be a future direction of your research if you so choose. Okay, so as many of you have maybe heard about or read about, there's one of the sort of really big open questions in physics and astronomy is this coronal heating problem. So the sun is, like many stars, has sort of a lot of things going on. Inside it has a core where fusion is happening. Then you have a convective, or a zone where you have radiation as sort of the dominant energy transfer mechanism. Then you have a region where convective currents are really important for transporting energy. And all of this is happening sort of within the solar interior. Then we hit the solar surface, which is what's known as the photosphere. So the photosphere is the region we can actually see with our naked eye. It looks like this in sort of visible wavelengths. This is where you see sunspots. So if you've ever heard about sunspots, these are sort of like dark regions on the solar photosphere. And this photosphere is around 6,000 degrees. So typically when people say, so the sun's temperature is 6,000 degrees, this is what they're talking about. And this is sort of the outermost layer of the solar interior. So everything above the solar photosphere is known as the atmosphere. So the next layer, oh, there it goes. And the solar atmosphere is known as the chromosphere. And it is still around the same temperature, like around 6,000 degrees Kelvin. So here on the left-hand side is a plot of height of the solar atmosphere versus temperature. So we see the photosphere around 6,000 degrees, the chromosphere is also around that same temperature. And then maybe like slightly hotter. And then we move to the outer atmosphere, which is known as the corona. So between the chromosphere and the corona, huge jump in temperature. So you might have seen this on the bottom. The chromosphere, here it's at 60,000 degrees. And now we hit the corona and we're 1 million degrees. So we have this really thin layer, which we call the transition region. A lot of sort of different things change within the transition region, and we see an immense amount of heating. So the transition region is a very thin region. It's a couple hundreds of kilometers, maybe even less, depending on sort of who you talk to and how you define this. And sort of between the chromosphere and the corona, we have this multiple orders of magnitude jump in temperature. So the sun's outer atmosphere is 1 million degrees. So this is the region that Parker Solar Probe is flying through. And one of the like big outstanding questions in the field is sort of, how is the corona heated? What is sort of happening in this transition region to cause this huge jump in temperature? How does this connect to sort of the processes happening in the solar interior? And most importantly, for what us on Probe work on, is how does this connect with what's happening in the solar wind? So there's lots and lots of work trying to understand this. Some of the main sort of candidate ideas are perhaps sort of fall into two categories, either sort of resonant heating processes where you care about waves and the interactions between waves and particles, versus sort of non-resonant or stochastic processes where things are heated via random fluctuations. And people have sort of lots of thoughts about this. And it's like a really large open area of study. Also lots of sort of arguing about this, like a couple hours ago in this meeting I'm at. Okay. I was just talking about energetic particles. So as I mentioned, PSP is really interested in understanding sort of how are these energetic particles accelerated. So these are observations, I'm going to pause this for a moment, from sort of a combination of instruments. So in the inside, we see the sun and the corona. So the green portion is an observation in EUV wavelengths. So this is actually showing sort of the outer atmosphere, the coronal region. And then we have observations from coronagraphs. So coronagraphs are instruments that make sort of artificial solar eclipses. So they cover the sun. So you're just seeing the corona. As you might notice, there's sort of a gap here between like around 1.5 solar radii, which is the coronal part we image with EUV observations, and the innermost boundary of the corona. So this region known as the middle corona, we have very few observations of it. But if you're interested, there's a new mission that just saw first light called Punch, PI'd out of SWIRI in Boulder, and they're making observations of the middle corona. So they're going to help sort of like close this gap. But so we have sort of these coronagraph observations, and what we can see here is, you know, you see sort of the ambient solar wind, and then we see these huge eruptions of plasma. These are the coronal mass ejections. And as we were just talking about, and I mentioned, they're a really important mechanism for sort of particle acceleration. And that is important, again, for space weather impacts. So there's a lot of sort of work being done to understand how are these energetic particles accelerated. Okay. We're also interested in studying how the ambient solar wind is accelerated. So as I showed before, so there's sort of various solar wind speeds depending on what structure you're associated with. But one of the things we don't actually understand is how is the solar wind accelerated to the speeds that we see. Okay, so here are some observations of the sun. So this is, again, observations in EUV wavelengths. So we're seeing the outer atmosphere. Okay, so you can see lots of sort of different regions here. This is sort of like that magnetic topology I was talking about. We have these dark regions known as coronal holes, these brighter regions known as active regions. You can sort of see there's loop structures associated with the magnetic topology of the like actual solar magnetic field. We have some of these, some regions where it looks like things are sort of like outflowing. These are sort of regions of open field lines where the solar wind can emerge from. And I like this video because the coronal holes make us smile. This time period became like really famous because it looks so cute. But one of the things that we do know is that the solar wind emerges, needs to escape the sun, it needs to emerge from a region of open field lines. But as you probably can guess, the sun has gravity. So the solar wind needs to be accelerated such that it is able to escape the sun's gravity. So very similar to how on Earth you can calculate an escape velocity by just sort of setting the gravitational potential energy equal to the kinetic energy. So, 1/2 mv squared, calculate what velocity you would need to escape Earth's gravitational field. You can do the same thing to calculate what velocity you need to escape the sun's gravitational field. What we see is that the observations of the solar wind don't really like match necessarily what you would expect from just purely escaping gravity. There has to be some other way that the wind is actually accelerated. And so there's sort of a couple of different proposed mechanisms for how the solar wind is accelerated that people are interested in studying. Some of them are associated with magnetic reconnection processes, specifically one called interchange reconnection. Some other sort of acceleration processes are associated with turbulence, this idea that you can sort of have random fluctuations that can transport energy from really large spatial scales to small spatial scales to sort of heat and accelerate the solar wind. This is a huge sort of open area of debate where we don't really know what's going on at all. And there's a variety of people who have a variety of different theories that we need to test observationally. So PSP is really interested in sort of understanding how is the solar wind born, how is it heated, and then how is it accelerated throughout the inner heliosphere. Okay, and then as I mentioned, there's this dust-free zone. So probe makes measurements of dust from the antennas on the Fields instrument. And some recent papers out of the group in Boulder, led by David Malaspina, have sort of detected sort of the dust-free zone in the inner heliosphere, as well as some observations from the WHISPER team, that white light team out of APL and the Naval Research Lab as well. So this had been theorized for many years, but never sort of observationally confirmed. So this is one of sort of the cool observational confirmations of theory that Parker Solar Probe had. Okay, and then lastly, at Berkeley specifically, and a lot of what I work on is thinking about turbulence or heating processes. So one of the things that we want to do with our space missions is think about sort of what is physically happening. And oftentimes we want to think about how that physics can tie into the physics of other different types of systems. So as I've mentioned in this presentation, as you probably already know, sort of the sun is a plasma, the corona is a plasma, the solar wind is a plasma. And folks in sort of different branches of physics are really interested in understanding the processes that happen in plasma because fusion and because energy and because we want to do a variety of things with plasmas that you can't do with sort of other states of matter. And so space is a really good place to study the processes that happen in plasmas because it's so large. So a lot of the times lab experiments are sort of constrained by sort of energy budgets, the power they can input into their experiment and the size of their experiment. So you can only test sort of parts of different types of theories or specific spatial scales for different types of theories. But in space physics, we have, space is very large, so we can test theories on a variety of different sort of length and spatial and temporal scales. And so there's a lot of work being done to sort of understand sort of the turbulence that is going on in the solar wind using Parker Solar Probe observations, as well as how this leads to sort of different types of heating processes. So that's what's showing here. So there's a lot of work in our group at Berkeley. These are just some plots that probably mean nothing unless if you've looked at turbulence plots before. But the moral of the story here is that we were able to see that the waves could transfer energy to the particles through resonant interactions, thus heating the solar wind. And there's also lots of work done to make these sort of pretty pictures through simulations of turbulence. And you can see here that there's sort of these generations of what we call eddies, where they sort of look like things that are sort of like spiraling. And what you can see from these structures is that one, there's a variety of spatial scales, meaning some things are smaller, some things are larger. And if you run your simulation through time, you'll see that the sort of the larger eddies break down into smaller eddies. And so this transfers energy from large to small scales and then that energy can eventually dissipate and heat your plasma. And so these are things that people are really interested in studying, both from sort of a numerical and modeling perspective and from an observational perspective. Oh, and I guess there's one more slide. We also work on studying sort of waves and sources associated with the solar wind. So we see all sorts of different wave structures in the observations that we see. So these are some radio observations from the field suite, where we can see all sorts of different types of plasma waves in the solar wind. And we're also interested in doing using a combination of observations and modeling results to sort of trace topologically on the surface where the solar wind actually comes from. Okay, and I think, no, it's not my last slide. Okay, got a couple more slides, but sort of these are some of the open questions that we're interested in studying. And so, as was mentioned, Probe launched in 2018. Some of you have probably heard about the solar cycle. So the solar cycle is this sort of 11-year temporal period where the amount of solar activity that we have starts at a minimum and then increases to a maximum around where we are right now, and then goes back to solar minimum again. So PSP was launched like just before the start of solar cycle 25. Our nominal mission ends this September. We're sort of applying for funding now for the extended mission. But so PSP has gone and studied sort of the rising phase of the solar cycle up to solar maximum. And hopefully through the extended mission, we'll be able to study it all and further probe all these open questions I was talking about through the declining phase of the solar cycle. And the reason this is so important is because the magnetic topology looks very different. So at solar minimum, the magnetic field is much more stable, far less dynamic, looks a lot more like a dipole, rather than at solar maximum, there's sort of a lot more complexity associated with the field, which means that sort of the solar wind sources are more complex, the heating processes, there's far more energetic particle events that we can study. And so being able to sort of extend the mission through the rest of solar maximum through the declining phase will allow us to further probe these questions. Okay, this is the last thing I'm going to say. PSP, while it is flying through the sun's outer atmosphere and is really probing like what is happening low down in solar wind, it also allows us to do a lot of connection science. So as we probably all know, there's this thing called space weather, where what happens on the sun impacts has sort of geospace impacts here on Earth. And this is because of magnetic fields. So the sun has a magnetic field, it has the solar wind, and very often we have very highly energetic particles that are streaming from the sun, which is over here on the left, flying towards the Earth. And one of the great things about our planet, and one of the reasons that it's habitable, is we have a terrestrial magnetic field generated via sort of convective currents in our core. But the terrestrial magnetic field produces a magnetosphere, and this actually protects our planet from being bombarded by energetic particles in the ambient solar wind. So you can see here that this is the solar wind flowing towards Earth, and it's being sort of like repelled and pushed around Earth by something that looks invisible, but is actually what is known as Earth's magnetosphere. So this region where sort of the particles start to diverge and move around our planet is the region where the solar wind pressure matches the magnetic pressure from Earth's magnetic field. And this is sort of the boundary of our magnetosphere. And so this is like one of the ways that our planet is protected from sort of what's happening in space. Some interesting processes can happen where solar wind particles can actually be directly injected into our magnetosphere through magnetic reconnection, and we can get fun things like the aurora, but we can also get lots of problems for our power grid, for sort of GPS systems. We can have radio blackouts and that sort of thing. And so being able to sort of like predict when these things will happen is really important for sort of the safety of our space, ground-based, and like technological assets in general. And sort of, as I've mentioned before, to be able to do these predictions, we need to understand the processes that are sort of leading to these events, which means we need to really understand physically what's happening close to the sun. So PSP allows us to sort of make this connection between what is happening at our nearby star to what is sort of happening here on Earth, and how we can sort of better protect ourselves as a species. Okay, that is actually my last slide. I'm happy to take questions, or if people have something else they want to hear more about, yeah, just let me know.
That was fantastic. Thank you so much, Tamar. All right. Yes, a few claps.
Nice.
Actions. Awesome. All right. We do want to open the floor for questions, including from the team, if any of you have. But feel free to just speak up if you have a question.
It's
Kamal,
Mark.
anything in the Oh, go
I have
ahead.
a
Go ahead.
I have a question. Does the solar cycle have a relationship with the sun's temperature? Because you showed both graphs, but I want to know if they have a direct relationship.
Oh, there was actually one more thing I was going to say. I'll say after. Okay, so this solar cycle is associated with sort of the dynamo process that's generating the sun's magnetic field. We don't have a perfectly good understanding of how this dynamo process works, but people are able to make sort of predictions of the solar cycle, both based on dynamo models and sort of statistics of past solar cycles that are pretty good. So we know that this entirely relates to sort of the complexity of the magnetic field, but not it's not like the sun's necessarily like hotter during solar maximum, but these active regions, the plasma there is hotter than the coronal holes. But the fact that we have sort of this like really big jump in temperature between the solar surface and the outer atmosphere very likely has to do with the magnetic field. So in that way, they are connected.
Okay, cool. Thank you.
Mhm. The last thing I was going to say is if you want to access Parker Solar Probe data, you can do so in Python using PySpeedos. There's tons of documentation online. If you stalk me on GitHub, I also have some tutorials.
Actually, we have a Python workshop later today that Kamal's running.
What time is that Python workshop?
It's at 6 p.m. Pacific.
Thank you.
Yeah.
I had a question.
Mhm.
Are there any like instruments? I know you showed a bunch on the slides, but are there any on Parker Solar Probe that you work with a lot more than others?
Yeah, so I get paid by fields, the field suite. I do all the magnetic field modeling predictions for them. If I can go back to that. I have a list of them somewhere. No, I have this thing. Okay. But yeah, I primarily work with fields, which makes the measurements of the electric and magnetic fields, as well as the radio observations and the span instruments. They look like this. They were also built at Berkeley. So they make measurements of particle distribution functions so we can study things associated with particles. I have not once in my life ever looked at WSPR data other than to say it's really pretty. But I do use remote observations from other spacecraft.
I was going to ask what happens at the end of the mission for PSP.
Yeah, so the team has had lots of discussion about this. So normally we would apply for extended mission funding and the mission would continue sort of as was proposed for the extended mission. So there was sort of a variety of options of things that we could do, specifically in terms of our orbit. So as you see here, we had this orbit that went around Venus, and then now we're inside of Venus. And we're just like undergoing this orbit that goes out to around 150 solar radii and into like 10 solar radii. So one of the options was to just stay in this orbit. Another option was to move out of the ecliptic. So right now, if this is the Earth and this is the sun, we're like PSP is in that line in between them. But there's some interesting things that probably happen. We don't know. We've never gone from solar poles. But if you were to move out of the ecliptic, this would require some fuel to do that sort of propulsion. So there was like lots of discussion within the team. I think what eventually we settled on for the proposal was to just stay in the orbit. So theoretically, unless if we get hit by a bunch of dust or there's sort of other damage to the spacecraft has enough fuel to last like at least 100 years. As of now, that is what like all the orbital dynamics people say. So provided the extended mission is funded and nothing dramatic happens, like a dust hit to the spacecraft, it will just continue in its orbit taking observations forever. Yeah.
So I don't know if it's an issue on my end, but the screen sharing is just like a black line. So I don't know if you'll have to like
Sick.
stop sharing and then
I
reshare.
probably did something wrong. Yep. Wouldn't put it past me. But yeah, okay. So this was the orbit plot I was showing. Can you see it now?
Yes, thank you.
Okay, cool. Sorry about that. So yeah, so at first we were in orbits around like outside of Venus's orbit. Now we're within Venus's orbit. So we're just gonna stay in that orbit and continue downlinking data. Yeah.
Thank you.
You mentioned that Punch is gonna do observations of was it the middle corona you said?
Yes, they just had first light. It launched like a month ago, maybe a month and a half ago. They had like a press release about this. If you look up Punch and then like astronomy or something, you'll probably find it. But yeah, so they're taking they have a near field and wide field imager that are taking observations to sort of build a full picture of the heliosphere. What's unique about Punch is they're actually going to fill this middle corona region, and their wide field imager goes out to 180 solar radii. So they're basically going to have an image from the sun's surface, like almost to Earth. So they'll be able to study the propagation of coronal mass ejections, the evolution of the solar wind, basically from the sun to Earth from observations. And it's a single spacecraft with 4 imagers. It's a really, really cool mission. Yeah.
Okay, yeah, because Juan was working on some of the citizen science eclipse imagery.
Mhm.
That was also trying to fill that gap, right?
Yes, yeah. So one of the things you can do with eclipses is because oops,
Oh, great.
you're not constrained by the coronagraph. You can actually get observations in the middle corona. So there's a group out of Hawaii led by HelioHub. They're eclipse chasers. They like get on boats every time there's an eclipse and they take observations to study this middle corona region. Yeah.
Fantastic. We have a question from Aria.
Mhm.
Aria, go ahead.
Yes. Hi. Sorry. My Wi-Fi keeps
No, you're
going in
so
and out.
fine. You and me
Thank
both.
you, Tamar, by the way. That was really cool. You were talking about solar cycles for a second, and I was just wondering is past data of the solar cycle sufficient or detailed enough now? I mean, I'm just thinking, I feel like it would take a long time to be sure about results if you have to wait for at least, I don't know, like a couple solar cycles to be sure about any patterns you're identifying. I don't know if that's true or not.
Yeah, so not entirely sure I understood your question, but so okay, so yeah, right. So
I
this
think
is
it's a
just
matter of, what might be a one-off versus what we know kind of regularly
Yeah,
happens.
exactly.
yeah.
Because it would
Yeah,
take like a lot
so
of years.
yeah, so the solar cycle is 11 years. This is just a plot of solar cycle 25. In terms of like, this is a plot of the sunspot number. We have observations of this going back to like the 1800s. So there's lots of really, really good statistics about like what the solar cycle looks like on a macro scale. Obviously, PSP has only been around since 2018, so we don't have good coverage of the solar cycle. We would like to have coverage of one solar cycle, but then yeah, if the mission gets extended, it would just be around for multiple solar cycles and you could get better statistics for sure. Yeah. Hopefully that answers your question.
Yeah, thank you.
Mm-hmm.
Hey, anybody else? It's a rare opportunity.
I'm around. You can email me. That's my email.
What about Shine? Any other interesting news, or is there anything you're really kind of waiting to hear about?
Not particularly. Shine is a really cool meeting. I know Dan was mentioning this, but for any of y'all who end up going to graduate school in solar space physics, there are these 3 meetings, Shine, CEDAR, and GEM, that are fully discussion-based meetings, so there's no talks. So you just have these like 1.5 to 2 hour blocks of discussion sections on a topic. There's like 300 people at the meeting, and about a third of them are students. And typically the NSF will fund students to come. So it's a cool opportunity when you're in grad school if you decide to stay in the field. But yeah, it's like a good place to learn about what are the current sort of state-of-the-art things that are happening and what are the disagreements. But depending on your subfield, it can get like really heated.
Right,
but
that's the way it's actually been constructed, in that it's meant to be focused on discussion and
yeah,
not just typical
Yeah,
person.
there's like no talks at all, which is also nice for the attention span. Yeah, but it's a
Have
lot
you
of
been going for
chatting.
years since being involved in PSP? And
Yeah, this is, well, actually, I guess this is my third year in grad school. So yeah, this is the third Shine I've come to.
that's fantastic.
Mhm. It used to be in Hawaii every year, but now it's not. Sad.
Okay. Is Cedar's more focused on space weather? Is it?
Yeah, so GEM is a magnetospheric modeling meeting, and then CDAR is an ionosphere meeting, but they're the same style. The NSF funds about 80 students to go to each of these meetings, and then they're completely discussion based, no talks.
Got it. All right. Team, anybody else? Any? This is
My last
great.
question was what maybe causes the coronal holes?
Oh, yeah. So coronal holes are, so the reason that they're dark is because UV observations are essentially a measurement of some combination of the density and temperature of the plasma. So they're dark because they're really cold relative to sort of the rest of the plasma. But the reason they're cold is because they're regions of open field lines. So you're actually directly connected sort of lower down than you're observing here, rather than these active region loops like extend outwards from the outer corona, and they're very hot, which is why they look bright in these observations. But I guess to directly answer your question, they're caused by the magnetic field structure.
Related question. Sunspots are always supposed to come in pairs,
Yes.
but sometimes it doesn't look that way. Is it because
So the sunspot itself doesn't come in pairs. It's the okay, they typically come in pairs, but the pair thing you're talking about is if you look at the magnetic field observations of the photosphere, you'll see a pairing of like positive and negative polarity magnetic fields because these sunspots are typically on the photosphere, typically associated with active regions further out. So it's like a loop structure where like the magnetic field goes like this. So there's one sunspot that's like in polarity and one sunspot that's out polarity to like form that loop higher up in the atmosphere. So I think,
but so in that image there though, you on sort of the bottom middle, it looks like there's 3 sunspots. So
yes.
my first guess is okay, one's missing, but clearly
Yeah,
I'm
it can also be two sets of loop structures. This is a
okay.
very low resolution video. Yeah, we need to look at the magnetic field to see what was happening there. It's very low res. But yeah, it's probably like 2 loops where one of their foot points is shared.
Yeah, right. Okay. I've seen that before.
Like I think you can kind of see it there, maybe like that
Yeah.
loop and that loop.
Very cool. All right. Well, we're up on 4 o'clock. So unless there's any other questions, good dinners and after hours stuff at Shine.
Yeah, there's 1 hour left and then dinner. Thank God.
All
Yeah,
right.
the whole going to a meeting going till 8 p.m. thing is a little bit rude in my opinion, but it's fine.
Yeah. All right.
Yeah.
We'll give you back that time. Thank you so much, Tamar.
Yeah.
Absolutely fantastic. Really
Cool.
appreciate it. We see you're on HelioHub now too, the Discord.
Yes, I joined Discord.
Okay,
Discord's
well,
scary, but I did join. So yeah, if
make
you
sure-
need anything, let me know.
let's make sure Tamar is labeled as an expert.
Oh God.
And
No,
feel
no.
free to chime in. Yeah. Or connect
Okay.
with Tamar on Discord. All right. Well,
Sounds
thanks so
good.
much,
Bye.
everyone. Take care. Bye.
Thank you.